Hello everyone and welcome to today's webinar. Thank you so much for joining us. A few notes before I get started. Audio is provided via the GoToWebinar application over the internet, so please enable your speaker in all places. The application has muted your microphone, so I cannot hear you. However, if you have any questions during the webinar, there is a questions tool at the right side of your screen. You can use this to type in any questions throughout the webinar, and I will read and answer them if time permits. If time does not permit, then I will email you your answers to your questions. Today I'm going to talk about how you can reduce project costs by improving safety lifecycle data flow. And you can do this using a safety lifecycle tool that is fully integrated like Excelentia is. Before I get started, I'm going to introduce myself. My name is Kate Hildenbrandt. I'm a sales engineer here at Exida, and my role is to basically ensure customer success by providing training and application support for Excelentia and our other tools. If you have any questions for me that you want to email me directly, my email address is right there. I do want to note we will send these slides out at the end of the webinar as well as a recording of the webinar. A little overview of Exida. We are a leader in functional safety tools, consulting, and assessments. We believe the three of these can bring a deep knowledge and understanding to your project to help you achieve safety while optimizing your process. We also have tools and consulting for alarm management and cybersecurity. Exida is ANSI accredited certification body for functional safety and cybersecurity. We have many active members on functional safety committees, and we do have global locations. So hopefully you can find an Exida professional close to you. A little bit of an agenda. Today I'm going to give a high-level overview of the safety lifecycle. And then for each task in each phase of the lifecycle, I'm going to go over the number of hours that might be spent doing this task using Excel or an in-house tool, or using a fully integrated lifecycle tool like Excelentia. So we'll go through the three phases of the lifecycle, and at the end I'll summarize the overall reduction in project costs that you could achieve by using a tool like Excelentia. So let's jump right in. Safety lifecycle overview. IEC 61511 defined the functional safety lifecycle to provide a method to analyze, implement, and maintain the safety instrumented system. This is from project scope definition to decommission. And so it's giving you a guideline that helps you to assess the inherent risk in your process, implement safeguards against any hazards that are possible, and then maintain your system to keep it safe. And as you can see on the left-hand side of the slide, this is what it looks like in the standard. It's often depicted as a top-down list, almost like a checklist of each task that you have to do to keep your system safe. Many companies, when taking this life cycle, strive to find a low-cost, consistent work process to take on these tasks. And in some cases, it can be overwhelming. But you want to find a way to consistently do it, have anybody do it, to efficiently do it. And in some cases, a low-cost solution might be Excel or an in-house tool. The problem with this is usually there is a tool specified for each task. And when you're moving from one analysis, say process hazard analysis, to another, you have to transfer key information from one tool to the next. Then if you should ever have to go back to a previous step in the life cycle, you're going to have to do this again. This is rework, and this is something that is going to take up engineering hours and add cost to your project. And so it's not ideal. In addition, an in-house tool can be great. You can specify it to be exactly what you want within your company. However, it often takes a lot of maintenance and development to keep these tools up to date, to keep them going. And often that falls on somebody who has other tasks that they need to do. And so therefore, use of a fully integrated safety lifecycle suite is the true low-cost solution. It provides a streamlined work process that reduces your overall project hours for each project that you do. Now, the way this works is that each task has a module or a tool, but it's fully integrated within one platform. And so even though we often see it as a top-down list, the safety lifecycle from a data flow perspective is actually a cycle. So any information that you put into your PHA, for instance, your causes, consequences, are important to your LOPA. The information you get out of your LOPA is important to your SIL selection and is documented in your SRS. You then hand that off to your design team to do your SIL verification, and then you have to implement the design. Then in the operation and maintenance phase, any failure data that you collect can be used as actual site data for future analysis. And so a tool that fully integrates, that keeps your information stored and moves it around as needed, is going to save you a lot of time and reduce your project cost. That's a big claim, so how can we prove this? We did a case study. We took a very small sample project of 50 safety functions, and for each task in the life cycle, we assumed how many hours it would take using a more traditional method, for instance Excel or an in-house tool, versus using a fully integrated tool like Excelentia. Once all of the hours were totaled up, we applied an hourly range from $75 per hour to $150 per hour to give an idea of how much you could actually save using a tool like Excelentia. So let me dive into the details. Phase 1 of the safety lifecycle is the analysis phase, and it includes a certain number of tasks. I'm going to give you an idea of the tasks and show you how you can do this with a fully integrated tool. And so first, you start with your process hazard analysis. In this step, you're going to brainstorm possible hazards in your conceptual design. You're going to take your P&ID or your process flow diagram, and you're going to assess it for the inherent risk in your system. And then you're going to implement or see which safeguards are present that would protect against certain hazard scenarios. Once that's complete, you use that information in the layer of protection analysis. So now you're identifying independent protection layers that guard against these hazards. And that will help you then to, in this case, sometimes the independent protection layers are alarms that need an operator response. They might be a pressure relief device. They might be a safety instrumented function. And depending on the amount of risk that needs to be assessed, you then will have design criteria that goes along with each independent protection layer. That would be your SIL selection phase, and in that you determine the SIF integrity requirements for each SIF in your system. Then all of this has to be documented to hand off to the design team. And this document is called the Safety Requirement Specification. It's going to document all of your SIF design requirements for implementation, so you can hand that off for SIL verification to be done in the next phase of the safety lifecycle. So that's a lot that you have to do to analyze your system. What would this look like in a fully integrated tool? Here I have a screenshot of Excelentia. This is our PHA worksheet. And it basically tackles or guides you through a brainstorm of your conceptual design of your process. And so when doing the PHA, you're going to ask yourself a few questions. First, what could go wrong with my process? And a heads up, the answer to this question is a deviation. It's basically a challenge to any process parameter. So in this case, we have a reactor. What would happen if the reactor pressure gets too high or too low? If the temperature gets too high or too low? If there's too much mixing or not enough mixing? All of these information is your deviations, and in a tool like this, they would often be attributed to a certain node. So there is industry standard deviations that you would want to consider when looking at a reactor versus a turbine versus a piece of piping, and that is stored within the tool. Once you've determined what could go wrong, you then want to ask, why did it go wrong? And in a PHA, this would be your cause. This could be anything from a blocked vent to failure of your BPCS system, anything like that. So you want to identify why did it go wrong. And along with the cause, you have a likelihood. How often do we expect this to happen? Then you move on to how bad is it? And this is your consequence. I know that this could happen, I know that it would happen this often, and I know that this is the severity of the consequence. Together, the likelihood of the cause and the severity of the consequence give you your risk for this hazard scenario. Once you've determined the risk, you want to see what safeguards are present to guard against the risk. So how can we protect against this? Again, a safeguard might be an alarm. It could be a pressure relief device. It could be a instrumented protective function or a safety instrumented function. And so you're going to list all of these here and then say, now with these safeguards in place, what is the likelihood that this could cause a true hazard? And you have a resulting risk. From here, you want to ask, how can we learn more? And the answer to this question comes in the form of the recommendations. If you want to do more calculation, more evaluation to assess the situation, that would be done here. That, in a nutshell, is your process hazard analysis. You're going to come out of this knowing what are the high-risk scenarios and how could they happen. In a quality safety lifecycle tool, all of your inputs would be stored into a library. And so you can see here in this screenshot, all of the safeguards for my entire system are listed here, and they can be auto-filled or reused as needed throughout the analysis. This is going to help drive consistency. If something changes, like a tag number or a description, then you can change that here and it will change throughout the life cycle. Also, it's going to help this not become so much of a typing exercise. If you are using high pressure alarm PAH 500 again, you can simply link it and all of that information is right at your fingertips. So that is a time-saving element. Once your PHA is complete, you are ready to move on to your LOPA. And in this case, in this tool, you simply say, yes, I want to analyze this in the LOPA. I'm going to find this hazard scenario, runaway reaction from decomposition. This information then, the relevant information in the PHA, is automatically transferred to the LOPA sheet. So when you go to do your layer of protection analysis, you already have a sheet that is showing the hazard scenarios that you have identified in your PHA. It also transfers the causes over. So in this case, the cause would become an initiating event in the LOPA. This, again, comes directly from your PHA, and then you will add a frequency to the initiating event. Sometimes this is something that your company has standard, and you could just input the frequency yourself. In this case, if you don't have a standard frequency for a blocked vent valve or a BPCS failure, you can use the database embedded in the tool to look up that scenario and use an industry standard frequency. Also coming from the PHA, the safeguards become independent protection layers in the LOPA. And each independent protection layer is auto-filled here, and then you can input a probability of failure, or just like with the initiating event frequency database, there is a probability of failure database for each IPL. And so you can use that database to input industry standard probability of failure for each IPL. So the IPLs are going to help reduce the frequency of the hazard scenario and close the gap between your actual frequency and your target frequency, which can be seen at the top of the screenshot. You can see you have your tolerable frequency, which is often a industry standard or a company standard that you're trying to adhere to, and your actual calculated frequency from the tool given your initiating event frequency and all of your IPLs. The idea is that you want to close the gap, but any remaining gap there gives you your risk reduction factor. And so that shows you how much you have to still meet the target frequency. If you want to attribute the risk reduction factor to a specific IPL or a SIF, the tool calculates the required risk reduction factor for the SIF to achieve your target frequency. And so this is where you're essentially getting your design criteria. It will automatically calculate the risk reduction factor, which is attributed to a safety integrity level. So in this case, in order to meet the target risk, the risk reduction factor for this SIF is 100. And so the target safety integrity level is SIL 2. This is the design criteria that you would want to hand off to the design team to make sure that your system is meeting your target frequency. Once you've designed all of your SIFs and you have all of your SIL selection completed, you want to document that in the safety requirements specification. This is in the standard basically a document that summarizes your analysis as well as all of the requirements needed for each SIF that you can hand off to the design team so that they can adhere to those requirements. There's a lot of requirements in the standard, and all of these are shown in the template so that you can fill out and make sure that you are compliant to that standard. In addition, information from the analysis phase is auto-filled into the SRS template when needed in Excelentia. And so things like demand rate for your SIF, any ranges or set points, as well as your target risk reduction factor and target SIL level are auto-filled into the SRS template. It then automatically generates a report that you can hand off to the design team. It's going to be a consistent work process. You're going to save a lot of time in that report generation. You're going to recognize it and know where everything is, so you have your information at your fingertips. And then you can use that for the design phase of the life cycle. So let's summarize the analysis part. What are the time-saving features that a safety lifecycle tool gives us? First is the transfer of key information from task to task. In some cases, if you have just simply your PHA in an Excel tool and you're moving on to do your LOPA in another tool, you're going to have to re-enter that information. Then, God forbid, some of the information changes and you have to go back and do this again. With a tool like this, you're simply pushing a button. It's transferring the data for you into the right spot. There's no retyping. And if you have to go back and update something in a previous task, it's very easy to simply transfer it back again. Then there are libraries that capture user inputs that allow for autofilling and linking in other places during the life cycle, as well as automatically updating one tag number, one library item, and having that be consistent throughout. The tool provides databases and smart deviations that provide industry knowledge right at your fingertips, so you don't have to search around for initiating event frequencies or IPL, probabilities of failure, or what deviations would go with a certain node. And then, of course, the tool is doing automatic calculation and report generation for you. So, in the analysis phase of the life cycle, we determined that you could save approximately 500 hours for a small project of 50 safety functions simply by using an integrated tool. Now, I want to emphasize here that we did not assume that your actual analysis would take any less time. We're not trying to reduce the number of hours that you spend analyzing your system for risk. But in the transfer of key information, in the looking up information without databases, in the calculation phases, you are going to save some time by using an integrated tool. Then we move on to design and implementation. The tasks here start with SIL verification. This is where you're going to do your conceptual SIF design. This means choosing your equipment, your sensors, your logic solvers, and your final elements, as well as your SIF architecture, any redundancy that's required. You're going to choose your mission times and your proof test intervals, etc., to determine what your conceptual design is for a safety instrument and system, as well as to make sure that it meets your required SIL level. Once this is complete, you are going to document your conceptual design in a design safety requirements specification, where your original SRS is going to tell you what is desired or needed based on analysis. This SRS is going to communicate what the conceptual design is. So you're documenting all SIF requirements for implementation. Once all of this is complete, you have to program your safety PLC. And finally, you have to specify proof tests based on each device in your safety instrument and system so that you make sure that your devices are working as needed during operation. So how would we do this with a safety lifecycle tool? Well, first of all, one of the key features of the tool is that it provides the failure data for you. You're going to need failure rate data for each device in your safety instrument and system. What are your dangerous failures? What are your safe failures, etc.? This can be difficult to find without a tool like this. It is simply embedded within the tool for thousands of devices used industry-wide. And so you would just simply choose your piece of equipment from a drop-down menu, and the tool has that data embedded there. And so this is what your SIL verification tool might look like. Here you can model your SIF. This is a very simple 1 out of 1 to the logic solver, and then 1 out of 1 to the final element. When you're choosing your sensor equipment, again, you simply choose from a drop-down menu. Here you can also input the mission time, the startup time, your proof test interval, and proof test coverage. And you can specify, is this a high trip or a low trip? Can the PLC detect if my signal goes under range or over range, etc.? All of this helps in the design calculation that determines if you have achieved your required SIL level. This looks very similar for the logic solver. You're going to choose the logic solver you want out of the tool. You can input, if the database does not have what you're looking for, your own device with failure rates if needed. But again, here you're going to specify your mission time, startup time, your proof test interval coverage, etc. And the final element looks much the same. Here you're choosing a remote actuated valve, so you have your solenoid specified and then an actuator valve combination. You're going to specify, is it open or closed on trip? There's a lot of parameters that go into the tool to eventually determine your results. What is your achieved safety integrity level? What is your probability of failure on demand, your average probability of failure on demand, your risk reduction factor, and your mean time to fail spurious. All of this is automatically calculated by the tool. It's very fast. You can also see similar results for each part of the SIF, the sensor part, logic solver part, and final element part. Now, if you've modeled your SIF and you've chosen the equipment that you want and you haven't achieved your required safety integrity level, you simply go back, choose different equipment, perhaps add redundancy. All of the changes you would need to make to optimize your SIF are very, very easy to do and quick to do in a tool like this. So again, that is going to be a big time saver. Once your conceptual design for your entire safety instrument and system is complete, you have to program your safety PLC. And this is easy to do with a tool like this because all of the information that you need for this programming is already embedded in the tool. This includes your inputs and outputs and the relationship between them, as well as a lot of the information that goes into the design SRS. So, you know, your maintenance overrides, your bypass management, startup overrides, trip delay, etc. For your sensor conceptual design and your final element design, all of the things you need to know, the tags, the action, the set points, etc. are in the tool. And so this is something you can simply import from your Lifecycle tool to your safety PLC. This is a task that usually takes months to do. It can take months to do, and in this case it's not going to take nearly as much time. You're going to dramatically cut down on the time needed to program your safety PLC logic. Now, you know, you might need to customize, massage a few things, but something that would often take months is now going to take a fraction of the time. And then finally, you have to specify proof tests for your safety instrumented system. Every piece of equipment out there needs a functional test to make sure that, you know, periodically you want to go out and make sure that it's working as needed to keep your system safe. Often these proof tests are found in safety manuals for the devices. However, with a tool like this, you can generate a report that has all of the proof tests you need to do for your system in one report. This is done when you choose your equipment out of the SCRH, and again, a huge time saver. So let's sum up the design and implementation phase. What are the time-saving features with a tool like this? First, we have simple SIF modeling and equipment selection. So once you use the drop-down to select your equipment, all of the failure data is embedded, and so it does a very complex SIL calculation instantly. Along with all the other parameters that it takes into account, you're going to get an accurate read on your achieved safety integrity level. If you need to go back because you have not achieved that SIL level, you can simply choose different equipment, choose different architecture to optimize your SIF and achieve that SIL level that you need, and then move on to the next SIF. So this is a very efficient way to do your SIL verification. Finally, once that's all done, you have a template that produces your design SRS to communicate that to the operations team, the implementation team, and then you have automatic configuration of your safety PLC logic, because all of that information you need to configure your PLC is in the SIL verification and design SRS tool. Then finally, you need proof test procedures to move on to the operation phase, and you can have all of these at your fingertips very quickly with the report generation from the tool. So we determined that by using Excelentia for design and implementation, you can save approximately 800 hours on this phase of the life cycle, as opposed to using more traditional methods like Excel or an in-house tool. And finally, you have the operation and maintenance phase of the life cycle. A few things that you want to do in this phase: you're going to want to configure your safety instrumented system into a field collection database. Why? Because the standard says it's mandatory to collect field failure data and also to prove that you're doing your proof test recording. The idea here is that you want to validate your design and analysis from earlier on in the life cycle. So some failure rates were assumed, initiating event frequencies, probability of failures. All of this is great data, but it's never as good as your actual site data. And so you want to collect any field failures. You want to be able to use that to validate your design and also in future analysis. And so you're going to have that one database. You're going to have to configure your entire site into that database. Then you're going to have to perform the field failure and proof test recording. And you may have to prove standard compliance and be prepared for an audit at some point. And so how would you do this using a tool like Excelentia? The first step can be very difficult if you don't have a fully integrated safety lifecycle tool. You're going to need a list of all your devices, all their model numbers, all their locations within the plant. You're going to need a database of the proof test procedures, not only what you need to do the proof test, but records that they're all done, any maintenance activities. And then you're going to want to record if there is a demand on your process. If there is a hazard that happens, what independent protection layer guarded against it? All of this is information that you need to record, but how do you do it? With Excelentia, you can simply import your safety instrumented system into our SIL Stat module, as you can see here, which will allow you to do all of this. It's going to automatically configure your plant hierarchy, which includes all your addresses, all your devices, all your hazard scenarios, as well as any proof tests and maintenance activities and their schedules and intervals. And so that is a huge time saver. It's one import. Again, you might need a customize or massage, but it's going to take dramatically less time to set this up. Once it's set up, you can simply move on to actually recording the data. So this is what a proof test recording would look like in the tool. You have your procedure right there in the tool, and you can input any information needed directly into the tool. You're going to have your dates, who did it, perhaps a work order number, and you're going to record the proof test results right there. The tool will keep that in its database, and so you have proof that you did it, you have did it pass or fail, you have any corrective actions needed. Similarly, you can do device failure recording. You simply choose your device, choose the address, select the date that it recorded, and put in any failure information in there. What's the failure classification? What is the corrective action? Did you replace, refurbish? What date did the corrective action happen, etc. And then any comments that you need. And finally, if there's a process demand on your system, you want to record that for your initiating event frequencies. And so you're going to not only say, this happened in my system, but you're going to say, this is the safeguard or independent protection layer that guarded against it. This is important because if it wasn't the first layer of protection, you want to be able to say that that failed, and that could help you in the future. Well, once all this data is collected over a number of operating hours, you can have it in one place, and you can use that to validate your design and or fix your design to make sure it's safe. In addition, you can use actual site data for analysis in the future. If you use SILstat, you can actually take your data and give it to us, and we'll put it into the Excelentia tool so that you can use your actual data to do your design and analysis. And so, what are the time-saving features for the O&M phase? You have automatic configuration of your plant hierarchy into a field collection database, all of your information in one spot. And then you have ready-made proof test procedures and a recorder so that you can easily use the tool to identify your procedure and carry it out. Finally, you have simple process demand and device failure recording, which creates a site database. And all of this allows you to prove compliance to the standard, not only through proof that you have the database and that you've done all these things, but in the tool, each task has a report. If you need a PHA report or a LOPA report, you have your SRS and your design SRS. You have your proof test procedures and your life event data all on hand in one tool that you can show for proof of standard compliance. And so we determined in our case study that in the O&M phase for a small project of 50 SIFs, you could save approximately 300 hours in the O&M phase of the life cycle. So let's add that all up. We found that completing these tasks with Excel Earn In-House tool would take approximately 2,000 hours. But for users of Excelentia, these same tasks, if you use the full functionality of the tool, would take about 600 hours. In this case, depending on the hourly rate of the engineers assigned to each task, the tool would save up to $240,000 for a small project. So again, I said this was for a project of 50 SIFs. It is possible for a system in the process industry to have hundreds of SIFs. And so how do you extrapolate that? Well, we estimated completion of safety lifecycle tasks using Excel Earn In-House tools nearly 4 times more expensive than using a suite of tools like this. Again, if you're using the full functionality. So in conclusion, by taking advantage of the full functionality of an industry-leading safety lifecycle tool, you're going to dramatically increase the total number of engineering hours required and reduce your overall project budget. Now that sounds great, but I like to have a visual. So we put together a Gantt chart, and this one shows the time it would take, your schedule, using Excel Earn In-House tool to analyze, design, and implement 50 SIFs in your system. This does not include recording or any of the O&M tasks, but it does include your analysis and your design, as well as configuring your system into an O&M database. And this shows that this could take up to approximately 10 months for 50 SIFs. However, if you're using an integrated safety lifecycle tool, implementing those same 50 SIFs for the same task would take only 3 months. And so you can see how dramatically that impacts the schedule of your project, which is very cool. If you want to know more, there is a white paper on this subject that dives into all the details for each task and what we determined for the hour estimates. And that's called Reducing Project Lifecycle Costs with Excelentia. You can find that at exida.com. If you want to talk to me, you want to see how this applies to your system, you can email me and we could schedule a meeting. We can put in your hour estimates and see how this could affect your company, your system with your work processes. So that's it for that. I do want to mention we have some courses coming up with Exida Academy. We have FSC 100 happening in Chicago, happening in Anchorage, and online in the next few months. We also have a fire and gas detection design and technology course in Scotland, and we have SIL Selection and SIL Verification in Mexico City, and a burner management systems course in Stafford, Texas. And so all of that is coming up in the next few months. If you're interested, you can visit exida.com/training to sign up for those. And if you're into our webinars, you can follow us on Twitter at Exida LLC to see when the next one's coming up. If you have a suggestion for a webinar, please send it to academy@exida.com. We love to do webinars on things you're interested in. We want this to be of value to you, and so if you have any ideas, please send it over. And so that is it for today. If you had any questions, I can email you directly to answer those. But in the meantime, I hope this was helpful to you, and have a good day.